Hello, my name is Naz Najir, a Principal Sales Engineer with Oracle's Cloud and Infrastructure Solutions team. I'm here to talk to you about how we can leverage SQL and Silcon in your real-time analytics opportunities. SQL and Silcon is one of the new software and silicon innovations in the new SPARC M7 microprocessor. So why are we talking about real-time analytics and microprocessor technology? Well, the world has changed. We now live in a globally connected economy. Businesses are recognizing more than ever the traditional ways of attracting and retaining customers are no longer working. To compete and survive, businesses must build products and services that their customers want. Social media, smart devices, ubiquitous connectivity has changed the way customers buy. Businesses not only have to develop a deep understanding of their customers' current buying patterns, but more importantly, what trends will be influencing their next purchases. To respond to this, their business systems need to be fast so they can make decisions in near real time about what new products and services need to be rolled out in response to their rapidly changing customer buying patterns. The key to this business challenge is real-time data analytics, which is driving Oracle's investment in SPARC software in silicon technologies and in memory technologies. The goal of today's presentation is to provide you with a good understanding of these technologies, allowing for confident conversations with your customer on how SPARC M7's SQL and silicon can be applied to their real-world analytics use cases. For today's talk, we'll set the foundation with a quick overview of the software and silicon innovations in the new SPARC M7 processor, specifically SQL and silicon, internally called DAX. Then we will look at some real-time analytics use cases. The first will be the Oracle DB in memory. The SQL and silicon was designed specifically to dramatically improve analytic query performance when using the Oracle DB in memory option. The next use case will briefly cover some of the work we're doing with Apache Spark, which sits on top of Hadoop's big data analytics solution. Then we'll cover our recent release of the Open DAX API. After that, if time permits, we'll wrap up with questions and any other answers that we need to follow up on. Let's begin. To understand where we are today with our microprocessor technology, let's take a look at the history of microprocessors. 20 years ago, it was all about 64-bit addressing, needed for open systems. 10 years ago, it was about multi-core and multi-threads, virtualizations in the cloud. The next decade saw a convergence of specific software functions into the microprocessor to assist with the difficult problems in software engineering. Just over 5 years ago, Oracle acquired Sun Microsystems and embarked on a journey to co-develop hardware and software solutions to solve these difficult business problems. We've seen examples of this with our engineered systems in the past few years. Now we're taking this convergence to a new level by implementing key software functions into those microprocessor silicon. In this current generation of converged microprocessors, Oracle has delivered on its investment on SPARC microprocessor technology. 6 processors in 5 years, each with incremental chip performance and software functionality built into the silicon, primarily up to this point only focusing on encryption. The latest SPARC M7, however, is a breakthrough in hardware and software co-engineering. With this processor, we have not only increased general computing specifications, 32 fourth-generation core, 64 megabytes of level 3 cache, 4.13 clock rate. Compared to the T5, we're looking at 2 to 3x more throughput performance with 30 to 40% more single-thread performance and over 2x more encryption bandwidth. Plus, with software in silicon, we've added security in silicon, SQL in silicon, and capacity in silicon. And I'll cover these in more detail in the next slide. The first software in silicon feature is called security in silicon, SSM, and crypto acceleration. This comprises of both application data integrity and cryptography capabilities. Application data integrity, or ADI, features allow the microprocessor to be able to detect illegal memory accesses, either accidental due to programming bug or malicious due to hacking attempts like Venom or Heartbleed. ADI prevents data from being illegally accessed or possibly corrupted, all with very minimal system overhead. The next software in silicon feature is what we call SQL in silicon, internally known as Data Analytics Accelerator, or DAX. These are physical components designed to dramatically speed up in-memory calculations. They offload query processing, filter data, free up CPU cores for other processing. It has the ability to decompress in-memory data and scan it while using fewer CPU cycles and less memory bandwidth. The next software in silicon feature is what we call capacity in silicon. Oracle databases compress data upon loading to maximize data storage either in memory or on disk. The SPARC M7 processors features inline data decompression that offloads the CPU cores while decompressing the data as it reads and transfers it into the SPARC M7 cache. On the SPARC M7 processor, the SQL in silicon features and the capacity in silicon features have been fused together into the DAX engine. Now let's take a look at what these DAX engines are doing behind the scenes. On the SPARC M7 processors, there are 8 DAX engines, each with 4 independent execution threads, 32 execution threads in all, that sits between the DRAM, L3 cache, and other DAX threads. Each DAX engine frees up general CPU cores to run higher-level SQL functions, while it handles the lower-level functions common to analytic queries. Its location on the chip allows it to read directly from memory and place results on the cache so that the general-purpose cores can use it for consumption. This shared cache provides for ultra-fast communication. It can independently process unaligned database column elements of any size at incredible speeds. We've seen results up to 170 billion rows per second. Here's a quick walkthrough of a single DAX engine. On the left, each DAX engine has high-speed SRAM buffer where it keeps data that it needs to access quickly, such as decompression dictionaries or lookup tables. On the right, the execution unit can get input from another DAX unit, thus allow pipelining instructions, or from level 3 cache, which is how it communicates with the cores, or from DRAM memory. Because the DAX units are placed with MCUs or memory control units, they can get their data at full speed. In the pipeline, the data goes through multiple stages. In the first phase, the data is decompressed. The decompression units understand Oracle OZIP format. In the next stage, the uncompressed data is then unpacked through an operation called extract. For example, data might be needed to expand it into full words if the data was at byte or bit packed or run length encoded. In the next stage, the pipeline performs join, called Bloom filters, or evaluation conditions, or such as predicates that we see in a SQL statement. And these things may have things such as equal to, less than, greater than. And the last thing it does is it performs performance matches based on existing results of bit vectors. In the next stage, the resulting data is expanded into repeating decompressions. Then the output is packed, if it were expanded or unpacked initially, and then into the compact format it was originally in. Just as there are 3 input sources, the output can also be pipelined into other DAX units, L3 cache, or back into the DRAM. The decompression that we are seeing in the DAX is equivalent to 64 extra cores if we were to look at this on a normal processor. Here are some internal performance benchmark of the SPARC M7 processor versus an Intel X6 E5-E3 Haswell processor. Overall, you can see we're seeing about a 2x to 3x performance improvement on SPARC M7 versus Intel. This is primarily due to the overall general compute performance improvements that we've made. You know, more cores, faster clock rate, more onboard cache, faster memory, faster I/O bus, PCI Gen, and so forth. But the benchmarks that stand out are the ones that utilize the software and silicon features. For example, in the security area, you're seeing that's where we're using this silicon and secured memory, SSM, and that's where we'll get some huge performance increases there. For the Hadoop workload, where we're seeing 4x improvements, that is utilizing SQL and silicon. And in the in-memory DB area, the two areas where we're seeing 10x and 8x improvements, those are benefiting from SQL and silicon. So overall, we're seeing that the running analytics on the SPARC M7 with software silicon there's a tremendous benefit to analytic workloads. Now we'll continue with our use case examination. The first use case we will look at is utilizing the Oracle DB in-memory option with SQL and Silcon for your DAX real-time opportunities. When we look at how businesses store data to represent their business activity, there has long been discussions about which format is best. Should I use row format or column format? Bottom line is row format is optimized for OLTP workloads, and column format is optimized for analytical workloads. OLTP operations tend to access only a few rows, but touch all the columns. A row format allows quick access to all the columns in a record, since all the data for a given record are kept together in memory and on storage. Since all the data for a row is kept together, much of the row data will be brought into the CPU with a single memory reference. Row data is also much more efficient for row inserts and updates. Analytical workloads access few columns, but scan the entire data set. They also typically require some sort of aggregation. A columnar format allows for faster data retrieval when only a few columns in a table are selected, because all the data in that column is kept together in memory, and a single memory access will load many column values into the CPU. It also lends itself to faster filtering and aggregation, making it the most optimized format for analytics. In most organizations, both formats exist, and data lives in separate repositories or database. Row format for your operational data and column format for your analytical data. Typically, you have a complete ecosystem of applications and processes that convert this operational data into analytical data. These processes can have long run times and do not provide immediate feedback to the business on the current customer buying trends or behaviors. Up until now, we've been forced to pick one format or the other and suffer the trade-offs between either suboptimal OLTP or suboptimal analytics. Oracle DB in-memory option solves this problem with its innovative dual format in-memory architecture that combines the best of row format and column format to simultaneously deliver fast analytics and efficient OLTP. It provides both row and column format for the same data. Simultaneously active and transactionally consistent transactions. Analytics and reporting use in-memory columnar format. OLTP now uses proven row format, and this completely eliminates any stale data created by batch processing. As we've been discussing, the goal of a modern business is to become a real-time enterprise where analytics can run simultaneously with transaction processing on the same system to provide the most efficient decision-making. Oracle Database 12c, utilizing the in-memory database option, is designed to have the same database perform transactions at the highest performance and to transform analytic calculations that once took days or hours can now be done orders of magnitudes faster. This enables companies to make data-driven decisions, respond to customers' demand, and continuously optimize their key business processes. While the in-memory database option is platform agnostic, meaning that it can be run on any certified system and hardware, there are significant benefits to deploying it on systems that use the SPARC M7 processor. As we have shown in previous slides, the M7 processor has deep innovations to take the real-time enterprise to the next level of performance. In internal performance tests, we have seen this Oracle database in-memory option demonstrate 100x to 1,000x speed up for enterprise application modules, including eBusiness Suite, JD Edwards, PeopleSoft, Oracle SQL, and Oracle Fusion Apps. On the SPARC M7, leveraging its industry-leading memory bandwidth, DAX's ability to compress data at the same rate as scan-only, perform one-step scans, one-step range Bloom filters, and joins, it can take database in-memory query performance to new level. Here's an example of a typical analytics SQL statement and how it's processed by the SPARC M7 and its DAX engine. The statement has been color-coded to demonstrate which DAX functions are being used. So as you see, we select some, and in that statement there, both the DAX and the general purpose cores are being used. And then in the from statement, we see hash joins. That is being done by the core. And then we go to the Bloom filter. This is one of the key functions in the DAX pipeline engine. You're seeing that this is where the Bloom filter happens. Then we go into a where clause, where an item, specific column equals, this is specifically a filter that is done by DAX. It's a scan. And then we're doing a range scan, and this is another function that's being done by the DAX coprocessor. So you can see a typical analytics query is leveraging both the general purpose core, the higher level functions, and the low level analytic functions, such as the joins and the scans and the filters are being done by the coprocessor. Internally, we have seen results, like I had mentioned earlier, up to 170 billion rows per second by utilizing the DAX coprocessor. Now let's take a look at how a SQL statement that we just looked at executes on a, again, this is with the Oracle database in-memory option, how this statement would execute on an Intel platform versus the SPARC DAX platform. So in the x86 platform, what we do is we issue a read, and then because it doesn't have the fused-in decompression, we'd have to decompress that in-memory data, potentially doubling its size and possibly evicting cache needed by other processes or other threads in the CPU. Then we write that cache back to memory, then we reread that data, and then we perform scans using the normal SQL microprocessor instructions, which are SIMD, single instruction, multiple data sets. And then we write the results back to the processor. And when you compare this to a DAX pipeline, you're basically looking at the read, and because DAX has the fuse, compression, decompression, and the SQL functions built in, we perform all of those things that you see happening in the Intel platform, we perform that in one step, and then we write the results. So really fast performance. We're on a really fast, high bandwidth memory architecture. So on the DAX processors, these SQL statements are going to outperform Intel statements. To provide proof that the Oracle DB and memory option on SPARC outperforms the latest Intel, our internal performance and engineering teams conducted tests on both OLTP transactions and analytical queries on a single database instance using all the same features as Oracle database in-memory options on very comparable hardware configurations. On both systems, the OLTP and analytic queries took about, a half of the processing load of the servers, meaning that they taxed it about 50%. In this test, the SPARC M7 is compared to a 2-chip x86 E5 V3 server. On the analytical queries on the SPARC M7 processor, it's about 8.2 times faster than the x86 E5 V3 processor. Simultaneously on the OLTP transactions, the SPARC M7 is 2.9x faster than the Intel. In addition, the SPARC T7-1 server had better OLTP response times than the x86 servers. The results of this test were obtained by running a set of OLTP transactions and analytical queries simultaneously against 2 schemas, a real-time online ordering system schema and a related historical order schema configured as real cardinality database star schema. The in-memory analytics RCDB schema executed using Oracle database in-memory columnar feature. And as we've shown in earlier slides, running those types of workloads on the DAX provided the performance results that we've seen here. Internally, these results are posted on our benchmarks, our SAE performance benchmarks. Now, based on the internal testing on the previous slide, you can see that we would need 5 of the latest generation HP servers, 1 for OLTP and 4 analytics, to match the performance of a single T7-1. We thought it would be very interesting if you then did a TCO example of what this would mean. So let's take a look at that now. A 3-year comparative TCO of these 2 solutions show an infrastructure cost savings of $154K over 3 years. This only reflects infrastructure hardware costs. So that's hardware acquisition plus 3-year support, servers, racks, infrastructure, networking, OS, virtualization, management software, external storage. And these prices, when we're doing the comparative, were reported by third parties that we use to conduct these TCO analysis. Now, if we were to license both solutions for the Oracle database in-memory option, the HP solution would require, this is huge, 5.6 times the number of software licenses compared to the T7 solution. This is based on the number of cores, right? So the HP solution has 180 cores versus 32 cores in a single T7-1. This is a huge savings in this scenario. Now let's take a look at another prominent real-time analytics use case scenario, Apache SPARC and SQL in Silicon. So what is Apache SPARC? Apache SPARC is an open source cluster computing framework originally developed by the AMP lab at the University of California, Berkeley, but later donated to the Apache SPARC Foundation. Compared to Hadoop's 2-stage MapReduce paradigm, SPARC in-memory primitives provide up to 100 times faster for certain applications. The framework extracts the input data into forms called resilient distributed data sets, RDDs. These RDDs can be created from an object in the program, or they can be created directly from text file inputs. RDDs are immutable, which means that any changes to an RDD creates a new RDD. They reside in memory, thus reducing the traffic for immediate results. This helps SPARC achieve speeds that are up to 100 times faster compared to Hadoop for some applications.
So why is SPARC a good fit for DAX? Apache SPARC's in-memory constructs, the RDDs, can leverage the DAX primitive functions, with the scan, value and range comparison of array searches, select, filtering functions to reduce column and pattern matchings, translate complex lookups, extract, compress, decompress. The Apache SPARC applications that benefit the most from DAX are applications that are going to sort and search unsorted data, which both involve a lot of memory access. But also keep in mind that there are many SPARC applications that don't leverage RDD constructs and would not benefit from using DAX. Some of these applications would probably be things that input data comes in and there are a lot of modifications or matrix modifications. But in most cases, if it's a SPARC application and it's leveraging the RDD and memory constructs, it's most likely a good candidate for DAX. To show this, our internal engineering team developed a SPARC application to demonstrate the benefits of this accelerated performance on the DAX coprocessor. They built an application that builds 3D dimensional cubes. The values of each dimension ranges from 1 to 1,000, right? So you got three dimensionals, each ranging from 1 to 1,000. This resulted in a billion rows folded in cubes. Without DAX, that SPARC application took 38 seconds to build this cube. With DAX, it took 6 seconds, or roughly 6x faster. These are the SPARC application use cases we want to target. The third use case we'll cover today will be around the release of our open DAX API for developers. The reason I believe we need to highlight this use case is because it can provide a competitive advantage for third-party application developers to develop products with extreme performance that differentiates themselves from others in their market segment. The Open DAX API is really at the foundation of what we saw in the Apache SPARC use case previously. So what is the Open DAX API? It's an open application programming interface, or an API, to provide developers with access to the DAX primitives using programming languages that they're familiar with, like C, C++, Java, Python, SQL, so forth. And as I stated earlier, it was the foundation, the DAX API was the foundation that we used in this Apache SPARC use case. There are multiple ways that the developers can do it. We have multiple sets of APIs, but for this discussion, we really need to focus on how these are opportunities for our customers. So how does it apply to real-time analytics opportunities? Customers who, the primary target here is customers who are developing their own custom applications for data analytics. Traditionally, we see a lot of this type of work done in financial institutions. But as data has become more ubiquitous, more and more customers in other industries are using open source tools like Hadoop and SPARC to develop their own application. Speed to analyze this data, this vast amount of data, is a key selling point for SPARC, SQL, and Silcon, and how developers can really get the most out of data in a very highly performant way. So now one of the other things to mention is that one of the top jobs coming out of college today in computer science is the role of a data scientist. So analytics, being able to perform these kind of functions on a very high performance processor is key to moving this technology forward. Just a few points to note. The API is not finalized. We're still developing it, and we're providing more functions to allow developers to create more custom in-memory applications. To encourage our third-party developers to start developing with Swiss and DAX, we've created a SPARC development platform, a cloud, where third-party developers can ask access to get to this cloud. We have templates, we create virtual images, and they can go out there and actually start playing with these features. It's a very cool feature. If you're talking to any of your customers that are looking at software development, data analytics, and they want to start playing with DAX, please point them to our DAX cloud. Internal findings so far using the DAX API. We're seeing that Java programs can, using the DAX APIs, can run 5 to 10 times faster. On a specific test, up to 8 copies of these programs ran without any performance degradation. On a T7.2, performance levels out at 32 copies. The throughput, however, remained constant, and the response time increased linearly. And then, you know, one unique thing that we saw is there was no performance difference using this API between C and Java, which has typically been a problem with development, as Java tended to be a little bit slower. So these results are posted, again, on that Swiss development webpage, and please point your customers to there so that they can see the results and start playing with the tool themselves. So this is the untapped area of the use cases I've developed. And I think this is the one area or the use case that has the most potential for growth, right? We talked about the Oracle in memory option and what we've done there. But if we can start driving our third-party developers, our customers, to start using it, to start using DAX for their analytics, the possibilities have really opened up. The DAX operations can be applied to both semi-structured data, for example, JSON files or SPARC RDB. This tremendously expands the number of applications that can benefit from DAX. You know, their analytic functions can run 5 to 10 times faster. But even greater gains can be achieved if we can create new algorithms and some sort of data manipulation. This is essentially free. These things used to attack systems. Now, because we can be more creative with how we do processing, we can do things that typically used to cost a lot of processing. Here, for example, the complex queries that are no longer a drain on system resources. As we saw in the SPARC use cases, there were queries that these kind of queries are suddenly very cheap, taking just milliseconds to execute. This leads to super fast data cubes and potentially removes workarounds previously needed because of processing constraints. And we're also seeing that the universities, I talked about data scientists being the top role. So at Brown University, they're doing a lot of work with analytics, real-time analytics, and they are actually testing DAX with some code that they have developed, Tupperware and SStore. So looking forward to seeing those results. And again, I believe that this one area of DAX, the open APIs for third-party developers, ISVs, is a huge potential for long-term growth of the SPARC M7 platform. So that ends it for my talk today. You know, so we really just wanted to give you a quick overview of software and silicon, specifically focusing on DAX. We wanted to cover, you know, the top use cases. The Oracle DB in memory obviously is the top one, and we should move that forward in all of our analytic use case opportunities. And the other two are sort of related, the open DAX APIs and how we can really push our customers and our third-party ISV developers to start utilizing these functions for their applications. So with that said, if there are no questions, thank you for your time today, and I'll see you in the field.